All right, so we've so far been working on what we call separable equations and separating variables to solve those equations. We haven't looked at any applications of these yet, so we're going to look at one before we close out this section. These are a problem that show up, a type of problem that show up a lot towards the beginning of a differential equations class, and we call them mixing problems. The idea behind these problems is you have a tank or a container of some kind, and you're like pouring a solution into it. Usually the solution is salt water. You know, we have a certain amount of salt that's been dissolved into a certain amount of water, and it's being poured into this tank. And then there's some mechanism inside the tank that mixes it. So the concentration of salt is uniform throughout all of the contents of that tank. And then once it gets mixed, some of that solution is let out through a different, exit point. So like a little valve or a pipe or something like that. And what we do with these problems is, because there is, a solution entering the tank, it's being mixed, and then it's exiting the tank. The solution, or the actual concentration of salt or whatever the substance is in this fluid, is changing over time. And so we want to model the amount of that substance in this tank with a differential equation, which when we solve it gives us a function that can tell us the concentration of that substance at a given time. Okay, so the trick to this is to use this as our differential equation. Here, y of t is a function that represents the amount of our substance that's in the tank at time t. Dy dt would then represent the rate of change in that substance. Now, there's two rates to consider if we want to model this. There's the rate at which that substance is flowing into the tank, and then there's the rate at which it's flowing out. So naturally, the dy dt that we're looking for is the rate in minus the rate out, okay? Which we call the rate in inflow and the rate out outflow. So inflow minus outflow is how we set this up. Once we set this up, we can then try and solve this differential equation. So here's an example. A tank has pure water flowing into it at a rate of 10 liters per minute. So there's no salt in this water that's coming in. The contents of the tank are kept thoroughly mixed, and the contents flow out at a constant rate of 10 liters per minute. So the water is flowing out at the same rate that it's flowing in. Initially, the tank contains 10 kilograms of salt dissolved into 100 liters of water. How much salt will there be in the tank after 30 minutes? Okay. So the trick here is to try and figure out what the rate in and the rate out are. Now, when we talk about these rates, we're only talking about the rate at which salt is coming into the tank, not the entire solution, just the salt part of it. The fact that it says pure water here means that our rate in is 0 because there is no salt in there. It's pure water. The rate is going to have as its units kilograms per minute. We're measuring salt in kilograms and time in minutes. So 0 kilograms per minute. What is the rate out going to be? This is the harder one to figure out. Okay. So how do we determine a rate like this? Well, first of all, we want to know what the concentration of salt is in the tank. We're told that there's 10 kilograms of salt dissolved in 100 liters of water initially, and that's going to change over time. But the 100 liters of water is the thing I want to pay attention to initially. So if our solution, or our pure water, is flowing in at a rate of 10 liters per minute, and then the mixed solution is flowing out at the same rate, 10 liters per minute, then the amount of solution in the tank is not changing. In other words, we're still going to have 100 liters of water, or our solution, I should say, in this tank at any given time. Now, if the inflow and outflow were different, then that capacity of the tank, or the amount of solution in the tank, would be changing over time. But in this specific case, it's not. So we have 100 liters of water or solution in the tank at any given time. Okay? 100 liters of, we'll call it 100 liters of water. The amount of salt in the tank is changing over time, because as it gets mixed, some of it will flow out through this pipe at the bottom here. Okay, so we don't know, excuse me, we don't know how much salt is going to be in this tank at any given time, but we do denote it by Y. Okay. Ooh, excuse me. So this is going to represent the just the concentration. Call it concentration of salt at any given time, and we measure Y in kilograms. But then we have to consider how fast it's flowing out of the tank. It's flowing at a rate of 10 liters per minute. I'm going to multiply that, 10 liters for every 1 minute. Now notice I'm going to get liters canceling here, so I'm going to get a new rate which is in the form of kilograms per minute. And that's the kind of rate I'm looking for, because I want to find how quickly salt is flowing out of this tank. The 10 and the 100 do a little bit of cancellation, and I end up with Y over 10 kilograms per minute. Okay, so if Y is the amount of salt in the tank at any given time, then Y over 10 represents the rate at which it's flowing out of the tank. So my dy dt now is the rate in minus the rate out, 0 minus Y over 10, or just negative Y over 10. That's a separable differential equation that I want to solve, but I can write down a little bit more information as well, because we have an initial condition. We know what Y of 0 is. It's 10. And the reason I know that is because it says the tank initially contains 10 kilograms of salt. So at time t equals 0, I know exactly what Y is equal to. I'm going to try to solve this now. This is a separable differential equation. Notice that if I were to divide both sides by y and multiply both sides by dt, I get dy over y equals negative t over 10. I can integrate this now, and I'm going to get the natural log of the absolute value of y is equal to, this would be, when we integrate this, it's going to be negative 1/20th t squared. Let's put a y there, t squared plus c. Okay. And we can do kind of a few things to simplify this. First of all, the absolute value here is going to be unnecessary. And the reason for that is because y represents something that can only be positive. It represents the amount of salt in the tank. So there's never a case where the absolute value is going to be needed. We can get rid of it, and then we can take e to the power of both sides to get y by itself. Y equals e to the negative 1/20th t squared plus c. And we've seen already in an example in the previous video that plus c here, I can use an exponent property to write this as e to this times e to the c, which we just call that c. C e to the negative, let me write this as t squared over 20. Okay. Oh, sorry. I just realized I did something I shouldn't have done. I'm going to have to fix that. There was no t in this originally, was there? There was just a dt. I'm going to have to correct that. So this was actually just negative dt over 10, which means this guy right here is actually just negative t over 10 right there. That's going to simplify things a little bit. Negative t over 10 plus c, e to the negative t over 10. Okay, so now that we have this, I can solve for c using my initial condition. I want to plug a 0 in for t and set y equal to 10. So 10 equals c e to the negative 0 over 10, which would equal just c. C is equal to 10, which means my final answer, y of t, is equal to 10 e to the negative t over 10. Now, the question that it asked us wasn't just to come up with the function, but specifically to determine how much salt would be left in the tank after 30 minutes. So for that, I'm plugging 30 in for t and trying to find what y is equal to. So this means that y of 30, which would be 10 times e to the negative 30 over 10, which is the same thing as 10e to the negative third power, which if I were to plug that into a calculator, I'm going to get roughly 0.498 kilograms, because remember, we're measuring salt in kilograms. Okay, so the amount of salt in the tank has decreased from 10 kilograms all the way down to less than half of a kilogram over the course of 30 minutes. All right, so that's going to wrap things up for this section.